Hi guys. So today we're going to keep talking about linear programs. So can anybody remind me what did we do last week, on Thursday? What did we do on Thursday? Any volunteers? Yeah. Sorry? We looked at max flow, exactly. So we were looking at, so last time, we studied a particular optimization problem. It was particular in the sense that it was not just a linear program, but a special type of linear program. And we saw that for every flow, f, for every ST cut left and right, if we look at the value of the flow, then how can I compare to the capacity of the cut on the graph? How are these numbers compare? Right, this way, right? Sort of for any flow that you give me and any cut that you give me, it is the case that the value of the flow is upper bounded by the capacity of the cut, right? And so in particular, when you look at a graph, you can sort of eyeball some cuts, right? And these cuts will tell you, whatever the optimal flow will be, you cannot do better than that. But actually, we sort of did something more than that. We also proved the max flow mean cut theorem, which, what does it say? By the way, it's part of the theorem's name. What does it say? It says that while for particular flows and particular cuts you might have a gap, okay? If you look at the maximum flow and the minimum cut, then these two numbers are the same, okay? So we have max over all flows f. If you look at the value that you get is the same as the minimum over all ST cuts. Okay? And why are we recalling this? Because this is an example of something we'll look at today that is called duality. Okay? So we'll see that we can associate to every linear program a dual program such that any feasible solution of the dual program is actually a bound on the feasible solution for the original linear program. And the solutions to the two optimization problems, the so-called primal linear program and the dual linear program, are actually the same, okay? And this duality in the particular case of flows, takes the shape of cuts, okay? So that's why I'm sort of recalling this thing that we did last time. So what I want to do today is to first sort of start through an example to talk about duality, okay? And then we'll try to kind of take a step back and see kind of what's happening in a general case, okay? Sounds reasonable? Okay. But notice that here, crucially, there is a max and here is a minimum, right? So that's how they're dual. All right, so let's start by talking duality in an example. So I'm going to use the example that we had a full week ago when we first started talking about linear programs, okay? So if I'm not mistaken, so we had this example with the cart, right? You had to stash inside the cart either chestnuts or corn, right? You had 100 units of volume, right? And you wanted to maximize profit. So it was something like you want to maximize 2x1 plus 4x2 subject to the constraints. Well, first, non-negativity, okay, because you're actually selling things. And then we're saying that the daily demand was no more than 50 for, I don't know what it was, maybe chestnuts. And for corn, it was no more than 80. And then we had a final constraint that was saying you cannot sort of fit more than 100 things in your cart, right? And we also had a figure for this linear program because it has only 2 variables, and we can actually draw it in the plane, okay, by associating, say, that direction with x1 and sort of the up direction with x2, and sort of all of these, each of these constraints was giving rise to a half plane, right? So the non-negativity was saying, okay, stay in this quadrant. This upper bound was saying sort of stay in this side, right? And this upper bound shows, it's saying stay in this side, right? And then this other upper bound is this kind of line here that says stay in this side. So overall, kind of the feasible the feasible set of solutions was inside this region. And a week ago we said that because the objective function is linear, then it's just a direction it's a certain direction you want to follow, which is whatever the direction that is orthogonal to the contour lines, right? And the direction was roughly this direction. So this turns out actually to be the solution, okay? So the optimal point. And if I remember correctly, it was x1, x2 equals 20, 80 with value. So what's the value? Let's compute the value. So if I'm at 2080, what's the value here? You just have to evaluate it, right? So it's 2 times 20, that's 40, right? Plus 4 times 80, okay, that's 360 overall, right? Okay, so just to have some state, this was the example that we saw a full week ago. And the reason I'm putting it up is that now I want to talk about duality for this particular example, okay? Questions so far? All right. Now, the point is that duality is kind of related to this sort of certificates of optimality, right? So if I can exhibit a feasible solution, one feasible solution of the dual that actually matches any value, any feasible solution of the primal, then I know I'm optimal, right? Because we'll see later that we define the dual so that everything, all the feasible solutions of the dual kind of sit above all the feasible solutions for the primal, just like flows and cuts. Okay? And to motivate that, a full week ago, we actually saw some short trick to observe this is an optimal value. So what was that short trick? So how did we convince ourselves that this is an optimal value? We kind of did some clever manipulation of the constraints to convince ourselves that that was an optimal value. What did we do? So this was, again, a week ago. It was not in the, it was when we talked about linear programming in general. So if you remember, when we went over this example, at some point we said, okay, that's optimal by picture, but then algebraically we also checked it was optimal. What did we do? We did some sort of clever manipulation on the constraints. Yeah? 2 times the last statement plus 2 times the second last statement. Excellent. So for any feasible solution, all constraints have to hold. In particular, I can take combinations of the inequalities, add them up, and those are only constraints that hold kind of a fortiori, even more so, right? Because they're just derived from sort of these original constraints. In particular, I can write 2 times this inequality, x2 is at most 80, and add it to 2 times, the other inequality, which is x1 plus x2 is at most 100. Okay, and I will get an inequality that says 2x1 plus 4x2 is at most, 160 plus 200, that's 360. Okay? So this is just a constraint that I've derived from other constraints. But look, inside here, I have an expression that actually equals the objective function, right? So this is saying no matter what I do, the objective function can never be more than 360. But look, here's a feasible solution that has value 360, so it must be the optimum. Okay? And kind of this short certificate of optimality, essentially these magical coefficients, right? Feels like a bit of a kludge or like some algebraic trick. But it turns out that duality precisely tells us this is always possible. Okay? So now we're going to try to somehow derive, for this example, how someone could have maybe not necessarily guessed and eyeballed it, but can actually derived how one could come up with these coefficients, okay? And then we kind of take a step back from that, okay? So kind of now we want to understand where do these magical coefficients come from? Why do they have to do with some other linear program, okay? So let's do this thing more systematically. So what we're doing here is that to some extent we're considering a variable per constraint. That is the variable that once everything is said and done, one of them will be set to 0, right? Because we're saying don't consider this one, right? Another variable will be associated to the other constraint, right? Which eventually here we're setting to be 2, right? So I'm associating one variable per constraint. So you can think about that I'm doing y1 times the first constraint here, which is 1 times x1 plus 0 times x2 is at most 50. Right? So I could consider to multiply the first inequality by some unknown magical coefficient y1. I could also consider to multiply the second inequality by some other unknown magical coefficient y2. And then I would get 0 times x2 plus 1 times x1 is at most 80. I'm introducing the zeros to just kind of point out that, all of these kind of look the same, right? They just have different coefficients in front and different sort of coefficients on the other side of the inequality. And then we would have y3, some other magical coefficient, where we have 1 times x1 plus 1 times x2 is at most 100. Okay? And there we kind of eyeballed what these things should be. But let's say that I can't eyeball this because I want to try and understand what's going on. Let's try to add up all of these inequalities kind of symbolically, okay? I'm not going to try to guess why. I'm just going to keep it around and see what happens. So if I add them, and in order to add them, notice that I need to consider only y1, y2, and y3 to be non-negative. Okay, so I'm assuming that. Why? Yeah. Yeah, it flips inequality, right? Okay, so right now I'm just considering only non-negative multipliers. It could be a 0 multiplier that just means I don't look at it. For example, back there I'm not looking at the first constraint, okay? And but I don't want to flip inequalities, okay? So under that assumption, if I add them up, what I will get is, what is the coefficient of x1 that I will get? y1 plus y3. Excellent. So here I can write y1 plus y3 kind of times x1. Okay? So plus. So what is the coefficient of x2? Right, because y1 doesn't participate, right? Because, yeah, you multiply y1 times 0, so it goes away. Here I have a contribution of y2, and here I have a contribution of y3, right? So I have plus y2 plus y3 times x2. And then say, is at most what? What do I get on the right-hand side? Right, something, right? So I get 50 y1 plus 80 y2 plus 100 y3. Notice that it's kind of a parameterized inequality for any setting, any non-negative setting of y2, y1, y2, y3. This is a derived constraint, okay? So it's like a space of possible derived constraints, okay? Now, what is really interesting to me is what was important here was that I derive a constraint that is something that means something to me. Why does this constraint mean something to me? Because it is the objective function, right? This is what we're trying to maximize. So here, what I'm interested in, what I would like, is some constraints on y1 plus y3 and y2 plus y3, right? Because I want to kind of create the objective function through these constraints. What are those constraints? Yeah?
y1 plus y3 has to be 2.
Okay, so let's write y1 plus y3 equals 2, and the other one, y2 plus y3 is going to equal 4, right? These are the coefficients that I'm trying to target, right? So, and now, what do I want? What do I also want? Okay, so that's one thing. So this is, maybe like one says, say like this, so to get the objective function. Okay, so anytime y1 plus y3 equals 2 and y2 plus y3 equals 4, I will get some upper bound on the objective function, right? Because on the left I get the objective function, on the right I'll get something, depending on depending on the values of y1, y2, and y3. But which upper bound on the objective function do I want? The smallest, the best, right? So another thing that I want is I want to minimize this expression, like just this expression, this right-hand side, right? For any y1, y2, y3 that satisfies these left-hand things, I want to minimize that expression because it will give me the best upper bound that I can derive. That sounds like a linear program, right? So let's try to write it as a linear program. So let's write the optimization problem about the kind of coefficients y1, y2, y3. Okay? So what I want to do, I want to maximize or minimize. I want to minimize, right? I want to minimize a certain linear expression. Which linear expression? That one over there. 50 y1 plus 80 y2 plus 100 y3. Subject to certain constraints. Well, first, I need these multipliers to be non-negative, right? And then I also need to kind of match the coefficients. y1 plus y3 equals 2, and y2 plus y3 equals 4, right? This really looks like a linear program, does it? So notice that under these constraints, kind of by construction, any feasible solution to this linear program, it is a valid upper bound to the so-called primal linear program, right? We've constructed it that way, right? We're saying, take those constraints, multiply them by something, add up, right? Put constraints so that on the left-hand side we get the objective function, and on the right-hand side we get some upper bound, right? So any feasible solution to this linear program yields an upper bound on the original program. Now, the smallest according to this objective function, the, sort of the solution to this linear program will actually give us the best upper bound. Okay, right now it's not clear that this best upper bound should equal the solution there. Okay, it's actually a deep fact I will only state later, I will not prove it. But in this case, we can see that here what we had was the solution 0, 2, 2, okay? Which is the optimal solution to this linear program, okay? Where we assign the value 0 to y1, the value 2 to y2, and the value 2 to y3. Okay? So is it clear how we constructed a dual program? Okay, because now, I mean, in a moment it's going to get more general, so we need to understand this example well. So again, yeah.
We also implicitly use like x1, x2 greater than 0.
We didn't use it quite yet. I will use it in a moment. So it's a great question. Kind of where did these things go? Did I use them somewhere? Not quite yet, but we will in a moment, because there is a slightly better way to write this one. But good point. I'll come back to that in a moment. Yeah. Oh, sorry. Thank you. Yeah. So this should have been a 1, just like it was suggested. Okay. Thank you. Right, yeah. All on the left only x1s, and on the right only x2s. Okay. More questions? Yes. How do I know that I'm not losing what?
Like an optimal.
That is not clear, right? So, but I am getting an upper bound, right? So right now I'm just kind of guessing that it suffices for me to consider non-negative multipliers without worrying about what happens when I flip inequalities, okay? And however, you know, in this example and certainly in general, it is absolutely not clear that the solution to all of these space of upper bounds yields anything that equals that one. This is also known as the duality theorem that I will state later, but we cannot prove in this class because it's actually a pretty big concept. But all I want to convince you of right now, like that you should be convinced, is that when we construct a dual linear program, we do get a family of upper bounds, all of which are actual upper bounds on the original sort of objective function by construction, okay? And if I ensure that my coefficients are non-negative, I just add up things. I put constraints so that on the left I get the objective function, and on the right I get whatever upper bound comes, right? And depending on the y's, there will be some upper bound. Okay? Is this construction clear? Okay. So now I wanna deal with the fact that here we actually knew something more. We know that x1 and x2 are non-negative. We can actually, it is important that we use this fact to actually make the duality theorem true, because I can write a slightly more relaxed, sort of more, less stringent linear program here by using the fact that because x1 and x2 are non-negative, I can actually relax these constraints. What can I do? If I want some upper bound, it suffices for me to ensure, for example, that y1 plus y3 is what? Not equal to 2. I can actually write something weaker. At least 2, right? Why? Because if I have my right-hand side is at least y1 plus y3 x1 plus y2 plus y3 x2, if both of those quantities are individually or respectively greater than 2 and 4, then certainly I do have an upper bound. I mean, I have an even better upper bound, right? So I'm going to come back here and say that I can actually make this greater than or equal. Actually, that's a terrible place to write it. Greater than or equal suffices because x1 and x2 are non-negative. Okay? Right? Because they're non-negative, if I increase in the positive side the coefficient in front of it, I can only get something bigger. Right? So if by y1 plus y2 plus y3 is not equal to 2, maybe it equals 3, right? That's okay. Whatever I get on this side can only be bigger than the objective function, right? And certainly this one will be an upper bound to that, right? Because this one is only sandwiched in between. Okay? So here, for every variable xi that is non-negative, I can actually put an inequality rather than an equality. That's important for sort of the general transformation to make sense. With that change, it means that when I write down this linear program, I can actually not write equals 2, I just write at least 2. And here I don't write equals 4, I write at least 4. So, again, this is important. It's unclear why this extra flexibility helps, but so in the general case, this flexibility is necessary. Yes? It is related because up there, y1 plus y3 equals is multiplied by x1, right? So if x1 were to be negative and I increase the coefficient that it is multiplied, I get something smaller than the objective function, not bigger. So I have to stay to the right. I can only afford either to get the objective function or something bigger than it. I cannot sort of have an upper bound if I go below the objective function. All I want is an upper bound to the objective function. If the left-hand side of that inequality risks going below the objective function, I do not have an upper bound on the right. Right? Yeah, good questions. Okay. So, and also we should verify that the solution y1, y2, y3 equals 0, 2, 2 has value that is 360. I mean, that was kind of obvious from there as well, but now we're verifying it because, look, we have 50 times 0, okay, that's fine, plus 80 times 2 plus 100 times 2, that's exactly 360. And also, we should verify that it satisfies the constraints. Okay, so all the y's are non-negative. y1 plus y3 is 2, right, which is at least 2. And y2 plus y3 is 4, which is at least 4. Okay, so it is a feasible solution. In fact, it's also optimal. Okay, yes. But we're minimizing, right? So there's always you can think about there are these. I mean, they really live in different spaces, but kind of the primal and the dual touch each other at the optimum, right? And one of them is maximizing, the other one is minimizing. Okay, so now we're going to attempt to derive what happens in the general case. So I give you a general linear program, and I want to derive, for a general case, its dual. Okay? It's going to actually involve some notation. Okay? So you really need to be comfortable with this example. Right, but I hope it makes sense. So, all right. So in general, we start with a general linear program, right? So we have, say, we're maximizing some number of variables. Let's call that number k. So we have some coefficient c1 times x1 plus stuff up to ck xk. Okay, so that's a general sort of some of the ci may be 0, some of them will be big, some of them will be small, whatever. This is a general linear function. Such that now the original linear program that we have here is special in two ways. One, it says that all the variables that we talk about are non-negative. In general, it doesn't have to be the case. Some of them will be non-negative, some of them can just be whatever, right? And also here, it only considers inequalities, okay? So we should also consider the case of equalities, okay? But you might say, oh, isn't an equality two inequalities? Yes, but they have two different sides. And right now, we were doing our transformation according to a certain side, right? So it will be convenient to consider equalities as a separate special case. So the way we're going to do it, we're going to say, okay, look, there is some set n, okay, which is a subset of indices 1 through k that tells us which of the xj must be non-negative. Okay, so in general, this is the generalized first line, just like the one up back there, okay? Maybe all of them are non-negative, maybe none of them are. In general, to be some set of things that must be non-negative. Okay. Then we have kind of the constraints proper, right? The things underneath. And here we have two disjoint sets. We can call them either inequalities or equalities. Okay, so these are kind of the two index sets. It says, if your I sits in here, then we're going to write an inequality. If this I is if your index is inside this set, we'll write an equality. So how does a general inequality look like? Well, it will have some coefficients that depend on the I. So a, I, and then 1. Why? Why 1? Because it multiplies x1, right? And then a, I, k times xk, right? And then blah, blah, blah is at most bi. Right? Do we agree this is a general inequality? Right? How does a general equality look like? Does it look very different? It's the same, right? I just changed this one, right? So let me write it. It says ai1, x1, then blah, 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 aik, xk, and then at the very end here, instead of writing less than or equal, I write equals bi. Okay? So, okay, so we have k is the number of variables. We can call m to be the number of constraints, which is the number of things in I plus the number of things in E. Okay? And why am I not counting kind of these are constraints? Well, they are constraints, but kind of we treat them a bit differently. The same way that here you saw that they played a slightly different role, right? So this is just a general linear program. Do we agree? Okay. Now, for this general linear program, I want to sort of apply the spirit of this transformation to get the corresponding dual. By the way, if it hasn't already appeared in homework, it will, or even in exams. Deriving the dual from the primal is a standard question that shows up all the time in CS170. Okay, so I'll try to kind of spell out it's really a mechanical thing. So you just need to understand the mechanics of it, and then there's not much left to creativity. So rather than directly writing a dual, what I want to do is I want to try to kind of go through so before literally writing a dual, I want to try to kind of justify the dual by doing something like this, okay? So for every I that we consider an inequality, we're going to consider a new variable yi, right, that multiplies the inequality ai1, x1, so I'm just rewriting the inequality, right? aik, xk, less than or equal to bi. Okay? And because Because this one is an inequality, we're also going to assume that yi is non-negative. Then, for every I that is in the set of constraints that are equalities, we're still going to consider yi that multiplies the thing that looks like that, except with equal sign. So ai1, x1, plus blah, 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 and aik, xk equals bi. Okay, and here, we're not going to consider anything necessarily, okay, because it's an equality. It doesn't matter what we multiply with, okay? And then what did we do here? Here we said, okay, we introduced all these things. We figure out which of the y's need to be non-negative, and then we just add them up, right? We try to see what happens, right? That's what we did. So now, let's just add up all these things, and we'll get a left-hand side and a right-hand side, right? Now, so what will it... So are we together so far? I said it will involve some notation. That's because we're doing it in a general case. But I want to attempt to explain it because knowing it in a general case, I think it's good. Okay, so we'll add up things, and what we want to do is we want to collect according to xi, right? So we're going to have a sum. No, sorry, not to xi, according to xj, right? Because I we're using it to index constraints, and j we're using it to index variables. We're going to have a sum over j, right? Because here we're grouping according to xj. And then inside the sum, we have a summation according to I, right? These are all the y's that touched a particular xj with certain coefficients, right? Because there, the coefficients were either 1 or 0, right? So the expressions were particularly pleasant. In general, you pick up the constraint, so the coefficient. So here we sum from I belonging to either the set of inequalities or the set of equalities. And we have yi, right? Can anybody tell me what's the coefficient here? Right, kind of traversing either rows or columns of these things is exactly the only difference, the difficulty here, yeah? Aij, excellent. So here I put Aij, okay? And, okay, this entire thing is the thing that sits in front of xj, okay? Good. So that's what we get on the left-hand side. On the right-hand side, what I get is sum over j, bj, no, not sum over j, no, sum over I. Sorry about that. Because, look, we're summing over bi's where these are the constraints, right? So for I in the union of inequalities and equalities, so we have bi times yi. This is the general form of that inequality up there, right? Do you agree? Okay. Now, we're almost there, okay? So now I wonder what I want to erase. I think it's a useful state to keep, so let's kill that board. All right, so let's try to write the dual. By the way, that thing that I wrote is correct, but it's missing some things. We'll get back to it in a moment. We'll catch them as we write the dual in a general case. All right, so dual in general. All right, so let's try to write the dual. So do I maximize or minimize? Minimize, okay, minimize. All right, what do I minimize? You're pointing at things, but you should speak. What's the objective function? Yeah, so it's b1, y1, blah, 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 plus bm, ym, okay? So that's just this right-hand expression here. That's what we want to minimize, okay? That is analogous to that one up there. So you see here, these are basically all the constants that had appeared on the right-hand sides multiplied by the magical coefficients yi, okay? Now, subject to. Okay, so before, we kind of started out by putting down the non-negativities of y's, okay? And here, we pointed out that really the only yi's that we need to be non-negative are those that multiply inequalities. So here, kind of, I want to say for every I somewhere, I want to say yi is non-negative. Where does this I sit? Huh? Yeah, capital I, right? So these are only for the inequalities. I really need to bother to make sure that yi is greater than or equal to 0. Okay? All right. So now gets something kind of let's first do it the easy way. So let's forget about this issue of greater than or equal versus equal. Let's just first do the equal side, okay? What I want is I want to set this expression to equal to what? Cj, right? So I would like this expression to equal Cj, right? Because then I know that my right-hand side is an upper bound on the expression, right? Which is the objective function that I was trying to maximize. Okay? So let's write that first. I want to write that A1j, so let me kind of, I'm fixing j, right? So it means that when I fix j, I'm moving I inside this, okay? And I want to set that to equal to Cj, okay? So I have A1j y1. So this is, I want to write this very clear. A1j y1 plus blah, 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 up to mj yj equals Cj. Okay? And what I could do is I could say for j going from 1 through k, right? I could just say, you know what, just make all of them equal to Cj, right? That was what we did earlier, right? We just said, take each of the Cj's and set the corresponding linear combination inside there to be exactly equal to Cj, right? But then we went back and said, well, you know, x1 and x2 are actually non-negative in the original linear program. So actually we can afford for things that are non-negative to relax this constraint to just be at least Cj as opposed to literally equal to Cj, right? That's kind of what we did there when we revised. But now in the general case, only some xj's are non-negative, right? Some of them could be negative, and then there's no point for me. I mean, it's not right for me to kind of relax equals to Cj to at least Cj. So for what j's can I do that relaxation? Those in n. And for those not in n, I don't do the relaxation because I can't. Okay? So here, instead of saying for every j going from 1 to k, I'm just going to say, look, consider the j's that are not in n. For those j's, do set it equal. And for the j's that are in n, you get the same expression, and then you say at least Cj. Okay? Kind of, I'm discriminating what I do on the coefficient Cj depending upon whether xj was enforced to be non-negative or whatever. Okay? Okay? Now, what is the number of variables in the dual? It says here, by the way. M, right? M was, what was M in the primal? Number of constraints, right? So that's equal number of constraints in primal. What is the number of constraints again? So these guys don't really count as constraints. They're kind of special constraints. How many of these are there? There is k, right? There is as many as number of variables, because every variable either sits in n or it doesn't, okay? So is the number of variables in the primal. Okay? And actually, if you kind of step back and you just mechanically see what happened, it wasn't actually like a weird operation. What's happening is that we're saying, take the b's, stick them in the minimization for the objective function, right? So you take the constants, boom, you throw them in the objective function. You take your coefficients from before and you put them as constants, okay? And then what do you do with the coefficients? What's the transformation for the coefficients? And so this kind of should give you like a hint. So what kind of operation is the one that switches dimensions? Matrix transpose, right? So in the original linear program, the Aij form a matrix, right? That has height, number of constraints, and width, number of variables, right? That same matrix appears in the dual linear program, just transposed. Okay, because the number of constraints is actually the previous number of variables, and the new number of variables is the previous number of constraints. Okay, so kind of taking the dual as an extremely mechanical operation, justifying why kind of it looks like this. You kind of have this derivation in case you forget, right? But that's exactly what's happening. And for the equals and greater than or equal, this is just depends on sort of who was non-negative and things like that. Okay, but at high level, again, the constants become the coefficients in the maximization function. The things in the maximization function become the constants, and you take a dual of, the transpose of the matrix for the Aij. Okay? Questions about the general transformation? Yes? Sure. The question is, why do we care if whether a certain variable is constrained to be negative when I set this equality? So let's look at this. Let's look at this example here where we had 2 and 4. Suppose for a moment that I wrote a linear program where instead of writing 2 here, I wrote, say, just for a moment, I will write back 2 again in a moment, but 3. I write 3. Okay? So now I'm setting y1 plus y3 to be like 3. Okay? So, and this one will still be 4. So really, we're just finding for the smallest thing that is at least 3x1 plus 4x2. Is this an upper bound to the objective function that we had before? Well, it depends on the value of x1. If x1 is negative, 3x1 is actually smaller than 2x1, right? But if x1 is non-negative, if you have 3x1, certainly that is at least as large as 2x1. So whether I allow, say, for example, this combination to be greater than 2 rather than exactly 2 depends on the sign of the corresponding variable it multiplies. Okay? In this case, this particular example, both x1 and x2 were anyways non-negative. So that's why we could say that either of them could be bigger. Okay? And in the general case, you need to pay attention to that. Does that make sense? Yes?
How can you write this viewing like matrix notation?
Excuse me?
How can you write viewing matrix notation?
I didn't understand once more.
Write the viewing matrix notation.
Why we're not doing matrix notation? Yeah, you can. Do you like matrix notation? I like it too. But no, but the point is that it's a bit implicit. No, it's concise matrix notation, but I think right this way, one could be more explicit. In particular, some of the why it is helpful to be at this granularity is to distinguish these two type of constraints, right? So you're taking the dual of everything, but exactly what you're enforcing depends on the index, right? So at the matrix notation level, it would be a bit hard to express this kind of this subtlety. Okay, that's why I prefer to do it sort of explicitly like this. More questions? Okay, yeah. Excuse me? Non-negative. Yeah, yeah, non-negative. Yeah, sorry, I forgot to say that. So I stands for inequality, E stands for equality, and N stands for non-negative. You can also call them whatever you want, right? They're just sort of various sets. Okay, so this transformation shows that any feasible solution by construction of this linear program is an upper bound, is an upper bound on the sort of any other feasible solution of the original program. So all of these are basically sort of short certificates that tell you can't do better than this. And the best certificate kind of is the best certificate here. But whether that certificate is a certificate of optimality, that's something that it's not clear a priori, that sort of the minimum here equals the maximum there. It is actually a theorem that I will write maybe. I will write it maybe here, so we get rid of maybe this part. That's called the duality theorem. That says that if a linear program has a bounded maximum. But why do I want this assumption? What happens if a linear program is unbounded? What happens to its dual? Wouldn't be unbounded. Maybe it's infeasible, right? Right? Because I know that if I were to construct it, anything inside it would be a bound on the primal. But if the primal is unbounded, then the dual will just have no solutions. Right? So if it has a bounded maximum, then its dual has a bounded minimum. Right? Because when you minimize, it could also, where you go? When you minimize, you could also have no bottom, right? But this is saying that if your primal has a bounded maximum, then the dual has a bounded minimum, and the two optima coincide. Okay? And so the crucial point here is kind of the fact that these two things equal, okay? And yeah, it's not really something we can do in this class. We'll take it as a fact, okay? So oftentimes there will be nifty homework or exam questions that let you reason about what you can say about the primal or the dual, about finding certificates of optimality. So just keep this fact in mind. Now, as another example of duality, now we're going to actually see how shortest paths has its own dual. But before that, are we fine with the general? So sorry, it took a bit of notation. I tried to. Hi. There's an elevator here. I didn't know that. There's an elevator that opens there. What do you want to say? Sorry, it took a bit of notation. I tried to clean it up as much as possible. At the end of the day, we're doing something general. So what you're going to do, right? I'm going to erase some of these things. I don't want to write them again. Okay? Yeah.
You say for all j is not n, can we go all the way to ym?
Oh, this should be ym. Sorry. That's ym. Thank you. Yeah.
How does this increase the efficiency of the program if you're just transposing the dimension?
It doesn't increase it. It just tells you about the geometry of linear programs. And in particular, you learn that kind of you can certify optimality using a short and easy to verify kind of proof. Okay? It was not clear a priori, right? Okay, so let's talk about how shortest paths interacts with duality. Also, it's time to say something stupid, right? Let's try something different, like some geography. Do you know what countries border Italy? But the Mediterranean Sea is not an answer, right? So it's not a country. What are the countries? Somebody said Austria. Okay. Then? Okay, Switzerland, France. Yeah, Slovenia, right? So. No, it's good. It does, right? So, in fact, there is one missing, even smaller than the Vatican. No, Monaco is it's off to their side in France, right? So, San Marino, right? Yeah. Right, San Marino is another microstate somewhere in central Italy. But yeah, so usually the ones that get forgotten are poor Slovenia and San Marino. It's okay to forget San Marino, maybe not Slovenia, right? So, and okay, so and which of these has Italian as a official language? Oh, Italy, yeah. Yeah, so Switzerland has Italian as an official language. San Marino also. And so does the Vatican. Oh. Okay. How many languages does Switzerland have as official? 4. What's the 4th one? It's not English, by the way. Okay, so people that said the 3, Okay, sure, there's the usual suspects. And what's the 4th one? No, that's German for them, so it's not Swiss German. So German, Swiss German are the same things in Switzerland. So I heard somebody mention Romansh, right? It's or Ladin. I don't know how it's called in English, but it's a derivative of Vulgar Latin. It's not Romanian; it's unrelated. It's spoken by maybe 20,000, 30,000 people in southeastern Switzerland in certain cantons. Okay. So anyways, so we kind of digress a bit. Okay, so in the middle there is Italy somewhere, right here, right? And and it goes down, right? So Italy is divided into regions. I guess not. It's a republic, right? So it's not a federation like in the United States. So these regions have only a certain amount of autonomy, but not sort of complete autonomy. There's 20 of them, and I guess the one that is close to me is the one where I grew up, right? There was one that contains Milan. So what region contains Milan? There's only 20. Yeah, but it's hard to guess if you know the number and they don't know the names, right? So it's not probability 1 over 20. Have you heard of any regions? So say some region. Tuscany is a region. Sicily is also a region. It's actually one of the more autonomous ones. Yeah, so Lombardy. It's so it's up here. Yes. It's up here. It mostly borders with Switzerland, Lombardia, and it's the capital of the region is Milan. It's a really nice area. Has mountains and lakes, and also it's one of the sort of economic engines of Italy. Traditionally, there's a lot of mechanical engineering, textiles. Actually, my own hometown, which is a pretty small town, it's maybe like 150,000 people. Even in my own hometown, sort of a traditional, industry, they make, I don't know, helicopters or like jets, or so it's very much based on sort of mechanical engineering and sort of heavy industries. So it's actually pretty affluent, certainly relative to the rest of Italy. Okay, there's some geography. Remember, Switzerland has four official languages. Slovenia exists. San Marino, you can forget, it's okay. And Lombardy contains Milan. Okay. All right, so much for that. So now we can relax a bit. Let's talk about shortest paths. So I think also the Vatican you can forget. It's pretty good. It's pretty small anyways. Duality of shortest paths. So when we have this undirected graph, and let's say for simplicity that we have positive weights, so what algorithm do we run? Dijkstra, right? Okay, and even though I'm not going to necessarily do it explicitly, you can actually write it as a linear program. What do you think? Are we going to max or min? We're going to min, right? Like it's going to be sum min LP. Okay, so its dual is interesting because it has kind of it's a maximization problem that has a physical analogy. So imagine that you have some sort of physical model of the graph, okay, where kind of two nodes, if they are connected, they have a string that connect them with a sort of physical length that is equal to the distance to the length of the edge between them. And sort of all these nodes are kind of connected by some sort of loose wire whose length equals precisely the length of the edge between them according to the weights. Okay. Now suppose that I'm interested. So and imagine that I have this kind of physical object and it's sort of sitting in a pile somewhere. It's on the table. And I'm interested in the shortest distance between, say, S and t, where s is a distinguished start and t is a distinguished end. How can I use this physical model to actually figure out the distance between s and t? Yeah? Right, so I can either take s in one hand and t in another and just go like this until something is taught, right? And what will be taught? The shortest path, or a shortest path, right? Another way you can visualize it is you can just pick up s and then you wait for t to start moving, right? It's the first time when it's kind of gets picked up by the graph. And what's curious about this physical model is because I'm maximizing something, I'm not minimizing. And by maximizing something, I'm finding the shortest path, right? So now I'm going to write sort of the A-linear program that sort of represents sort of this idea, and we actually prove that it corresponds to solving shortest paths. Okay? But does the physical model make sense, right? So you have this pile of vertices, they're connected by like loose wires, and the wires are length of the edges, and you can just kind of pick up s, and at some point when t starts moving, that's because you have a shortest path. Okay. All right, so the dual is as follows. So we're going to maximize a value that we're going to call x sub t. Okay, it's going to be related to the sort of target vertex t, subject to certain constraints. The constraints are going to be that the value that we associate to the source is by default to 0. And then, for every uv that is an edge, okay, I'm going to say that xv cannot be more than xu plus L of uv. Okay, that's the entire linear program. It may look a bit opaque, but now, what I want to do, I want to prove that the solution of this linear program actually equals the shortest path, okay? Actually, I want to use the rest of the board, so I'm going to sort of move this inequality here. So xv is at most xu plus L uv. Okay? Okay? So do we agree this is a linear program? Why is it related to that model? Because essentially, you can pick up, you can think about that I have xt, right? And I'm trying to maximize the distance of xt from every other vertex, right? Kind of from s, sorry. And as I pick up t, sort of distances between other vertices, they kind of go farther and farther from s, right? But I can't make them go too far away, sort of, because they're constrained by the wire, right? Any particular things that are tied by the wire, they cannot be farther away than LUV. They could be closer, right? But it cannot be farther, right? So that's sort of this picking up procedure I was describing is kind of enshrined in this sort of constraints. So now we want to, there's a claim that the optimal solution is the distance between S and T. Okay? So, say proof. So if we want to prove that, we have two things to do. We have to prove that the optimum is at least the distance between S and T, and separately it is no more than the distance between S and T. That's one way to prove that it's equal to the distance S and T. Okay? So let's first prove that this thing stops writing properly. All right. Let's first prove that xt is at most, sorry, it's at least the distance of a ST. So if I want to prove that something that I'm maximizing is at least something, it suffices for me to do what? So I'm maximizing, so this thing will kind of go up somewhere and achieve some high optimal value. Now there is a concrete value that I claim that the optimal value should either match or surpass, right? So what is one way to prove that this is the case? All I have to do is to give you a feasible solution with this value, right? The optimum can only be bigger, if anything, right? So I just need to construct any feasible solution where xt achieves that, okay? So let me put a star here. I mean that the optimum is at least that much, okay? Because now, let me exhibit a feasible solution that has that value, okay? The optimum can only be bigger. So what you can do is just set xv. So this is kind of the feasible solution that, by the way, I can't just set xt to be something. I have to set all variables and make sure that it is feasible, right? I can't just set xt to be something. So for every vertex v in the graph, we're going to set xv to be the distance from S to V, okay? Now, let's notice two things. First, x star t, by definition, is at least xt, which is a particular feasible solution that I just set, that right now I just said this equals, if I kind of set v to be t in this definition, it's just the distance of st. Okay, so that's fine, but I also need to make sure that it's feasible. So that's one side. It is feasible. So can somebody tell me why this particular setting of all variables is feasible? So here's where we use the fact that weights are, the lengths are non-negative. So to prove that something is feasible, I need to prove that these two things hold. Is it the case that the distance from S to S is 0? Okay, good. So xs, by definition, is distance of S from S to S, which is 0. Okay, that part is fine. So is it the case that whatever uv, xv is at most xu plus luv? We've used this all the time when talking about shortest paths, right? This is like saying that the distance from S to V, whatever it is, it cannot be worse than the distance from S to U and then going from U to V. Right? That's the usual kind of triangle inequality that we've been using all along when you have non-negative lengths, right? So that's definitely the case, right? Because we have xv, by definition, is the distance from S to V. This is definitely no bigger than the distance from S to U plus the edge from U to V. And then by construction, this is equal to xu plus luv. Okay? So notice xv is at most xu plus luv, right? So these particular settings of parameters certainly, says it's feasible. Okay? So whatever is the best choice within this feasible space, we can do no worse than that. Okay? Right? Some of you look confused. I'm maximizing. I just need to exhibit something that is at least this big. Okay? Here it is. Okay? All right. Now we have the other side. Okay? So let's prove that the optimum is actually no more than the distance from S to T. Okay? That would actually prove that what we're solving here is actually shortest paths. So in 2, we want to prove that xt star is actually no more than the distance from S to T. Okay, so one way to show that is derive an upper bound for any feasible solution. Okay? So let's see. Pick any feasible xv, so setting of the variables that is feasible. Just fix it, okay? One of them will be the maximum, right? What I do know is, because it is feasible, I know that xs must equal 0. I mean, that's true in every feasible thing. I also know a bunch of other things. And now what I want to do is I want to study, sort of pick a shortest path. So let me write it nicer. So pick any feasible, that one, and then also pick any shortest path okay, from S to T. And let's call it, say, S, then V1, then V2, blah, 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 up to, V, I don't know, n minus 1 and then T. Okay, doesn't matter how long it is. It is the shortest path, okay? So the sum of the lengths actually equals this thing, okay? So we know that xs must equal 0. xv1 is at most xs plus going from v1 to, make sure, from s to v1, sorry. Right? This is, I'm just invoking this inequality for the edge SV1. I also know that xv2 is at most xv1 plus lv1 to v2, right? And right? So I can write all of these inequalities for the feasible solution xv. Let's add all of them up. All of them, okay? So we add all of them up. Now things will cancel, right? Because xs will appear once on the left-hand side and once on the right-hand side. xv1 will appear once on the left-hand side and once on the right-hand side. So it can cancel all these things. Now these L's will stick around, of course. What is the one variable that will stay around? xt, right? So this will say that xt is at most the sum of all of the lengths on the path, which is L from S to V1, from V1 to V2, blah, 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 up to L from Vn minus 1 T. But what is this equal to? This is the distance from S to T. Why? Because I picked the shortest path from S to T. And the sum of the lengths is the distance. But look, this is an upper bound. Okay? This was any feasible solution. Okay? And I have analyzed a particular subset of constraints, those induced by a shortest path. And we're saying that, look, whatever xt is, it cannot be larger than distance. This is kind of similar to how we were deriving constraints earlier. Okay? We're trying to derive some upper bound. And here I picked a particular kind of smart way to derive an upper bound. So given the upper bound and the lower bound, they match. Actually, we've discovered that if you solve this linear program, the optimal xt equals the shortest path from S to T. Okay? And this is kind of the dual linear program to the primal program of shortest path. We actually didn't write explicitly because it's uglier. But this one is actually very cute and has a physical motivation. All right, so next time we'll talk more about linear programs from the perspective of zero-sum games.